All right, we are ready to get started. Okay, so in case you thought you were getting bored with stellar explosions, we have the entire diversity of things planned for this school. Today is going to be all about, today and tomorrow are all going to be about supermassive black holes. How many of you work on supermassive black holes? Okay. Okay, so yeah, a good number of folks. So today is your day. Right, so just to confirm tonight, well, today evening at 5, we will head over to the 11th floor after the afternoon session for social session with food and, kombucha, cold brew, whatever you like. Right, is there anything else? No, I think, yeah, that was the main announcement. So we will get started. So today, our first lecture will be on the theory of tidal disruption events. Our lecturer will be Itai Linial. Itai got his undergrad degree at the Hebrew University and his PhD at Hebrew University, and since then has been a postdoctoral fellow jointly between Princeton and Columbia, and will soon be moving to NYU as a Hubble Fellow. So and Itai will be telling us about the exotica happening in the centers of galaxies.
Okay. Thanks, Kishore. Hope this works. Yeah, so as Kishore mentioned, the last couple of days we've heard about how stars get destroyed as they deplete their nuclear fuel and evolve off the main sequence. Now we'll discuss how stars may be destroyed when they happen to be on unlucky trajectories that bring them close to a supermassive black hole in the center of a galaxy. So there's a lot to cover here. I'm not sure we'll get to all the things I've listed here. This also depends on how many questions you guys will have. We'll hear afterwards from Suvi on the observational aspects of this phenomenon called tidal disruption events, but I'll start by reviewing some of the basic theoretical components of this process. And yeah, we'll start. So we're talking about stars that get destroyed by supermassive black holes. So we know that centers of galaxies host black holes with masses of, say, 10 to the 5 solar masses to maybe 10 to the 9 or even 10 to the 10. As we'll see, this phenomena actually happens to prefer relatively low mass black holes. So nominally we'll work with a black hole mass of, say, 10 to the 6. And we're discussing a star. So consider a sun-like star with the size R star and mass M star. And this star will approach a supermassive black hole in the center of a galaxy on a nearly parabolic orbit. It will usually arrive from a distance. So its apocenter will be at a distance of roughly, and we'll get to that later, roughly 1 parsec. And if the pericenter distance, so the distance of closest approach, is small enough, tides destroy the star. So if this happens to be within some critical radius, tides become stronger than the star's self-gravity, and it gets distorted. So as it approaches this critical line, it gets slightly distorted. So maybe it develops this bulge from the tidal forces. But as it goes deeper into this region, it now becomes substantially elongated up to the point that it can no longer hold itself. This is the disruption. And then half of the star will be ejected onto unbound orbit, half will be falling back. So this is the tidal debris that will fall back onto the black hole, and we'll discuss how that might power a transient. So that's the basic picture, and there's a lot to unpack here, so we'll go step by step. Okay, so the first thing we'll want to discuss is what is this critical disruption radius. So tidal disruption radius. So we can estimate this radius fairly simply by simply asking what is the critical distance, and we'll call this critical distance RT, our tidal, at which the tidal forces from the black hole exerted on the star exceed its self-gravity. So essentially the question is, when does self-gravity become weaker than the tidal force? Okay, so how should we be thinking about it? So the self-gravity of the star, or the gravity per unit mass, is simply gm star over r star squared. So let's equate it for the critical radius. How should we be thinking about the tidal gravity? So as the star approaches the black hole, say at some point it's at distance r, the fact that the star has a finite size implies that different parts of the star feel different strength of gravity from the black hole. So this part gets pulled at some f of r minus r star. So this is the part that is closest to the black hole. And this is going to be slightly bigger than the gravity felt by the center of the star, which is going to be the gravity of the black hole at distance r. Okay, so we want to compare this to f of r minus r star, where f here is simply the gravity from the central black hole minus the gravity at the center. And we can just think about this as the derivative of the force multiplied by r star. So this is at RT. So if we take the derivative and forget about the factor of 2, everything we'll do here will be up to order unity corrections. So this will be g m black hole divided by r cubed, taking one derivative, multiplying by r star. So if we equate the two and solve for RT, so this is the radius at which these two forces become comparable. Let's see, so we have here cubed, and if we move this r star down here, it's also cubed, and the g's cancel out, right? So what we have here is r tidal cubed equals r star cubed times the mass ratio, the mass of the black hole divided by the mass of the star. So taking the cube, this is the tidal radius. So it's easy to think about it in terms of, say, a 10 to the 6 solar mass black hole and a sun-like star. So this ratio, 1 million to the 1/3 is, let's make it interactive. So I'll try to engage you guys, right? So this is factor of 100, right? So the tidal radius is 100 times bigger than the size of the star. So not really like I plotted it here on the blackboard. In terms of numbers, again, for our fiducial parameters of m black hole of 10 to the 6 and m star of 1 solar mass, I'm taking a solar radius. This comes out to be about 0.5 AU. And roughly, we can express this in terms of the gravitational radius of the central black hole. Turns out to be a few tens of gravitational radii, give or take. Okay, so that's the disruption criterion. We need the pericenter distance of this parabolic orbit to be within the tidal radius. If it's slightly outside, interesting things could also happen. Maybe only the outer parts of the star gets disrupted or get removed. But as long as you're a couple of times bigger than this r tidal, tides tend to be less important. This is also in part because the tidal force, which is this, decreases as the distance to the black hole is the third power. So if you double it, it becomes smaller by a factor of 8. Okay. There are another couple of nice ways to be thinking about this tidal disruption radius. One is noting that I could have stated it in a different way. So again, moving this r star downstairs, and we have m star over r star cubed equals the mass of the black hole over the tidal radius cubed. How should I be, what does this tell me? What do we have here on the left side? Density, right? So this is, in a way, the mean density of the star. And what do we have on the right side? So this is a bit less intuitive, but what it implies is the density if I were to take the entire black hole's mass and smear it evenly over the tidal radius. Okay, so some kind of effective density at the tidal radius. So we see that there's some density criterion where disruption occurs if the star approaches a distance from the black hole where this averaged density exceeds its own density. Okay, so this is another equivalent way to think of it. Sometimes it's even more useful. So this is approximately the density of the star. And this is, as we said, density of the black hole mass smeared over a sphere of size RT. Okay, another equivalent way to think about it, which is also sometimes useful, is to consider the orbital period. So what is the orbital period of a particle placed on the tidal radius? Right, so if I put a particle and let it circle the supermassive black hole, okay, so P orbital at the tidal radius is 2 pi square root of r tidal cubed over g m black hole. If we plug in r tidal cubed from this expression, we find 2 pi. Let's do this slowly. So r cubed, r star cubed times m black hole over m star over g m black hole. These cancel out, and we are left with 2 pi square root of r star over g m star. Okay, what is this? Right, so you might recognize this as the dynamical time of the star. So basically the time over which, say, sound waves cross from one side of the star to another. This is equivalent, expressed in terms of density. This is essentially 1 over square root of g times the average density of the star. So another way of thinking about what is the disruption criterion is essentially the star has some dynamical time, some typical time associated with how fast do perturbations in it propagate. And what happens when it penetrates the tidal radius is now the rate at which this tidal force changes on the star is faster than it takes the star to respond to it. So in a way, this is an equivalent way of thinking about the disruption process in terms of orbital period. Okay, any questions about 3 different ways of thinking about how stars get disrupted tidally? Okay, so the next thing we'll talk about is what happens following the pericenter passage of the star.
Maybe I could ask.
Yes.
Provocative.
Yeah.
So for a long time, people were debated whether the Okay, you're going to get it. You haven't talked about how deeply it's penetrating. Okay,
Yes.
So, okay.
Yes.
Okay. So whether, okay, all right, I'll let-
And I'm actually going to limit the discussion to betas of order unity.
Okay,
So
okay. All right, very
maybe
good.
we can save it to the
Very
end.
good, yeah, thanks.
Okay, so actually before we get to what happens to the disrupted material, I just want to mention some nice and simple results, which is also quite useful, which discusses the maximal mass of a black hole that can disrupt a star. So this is useful thinking in terms of these densities. So if I take a given star, it has a mean density, and I look at this expression, m black hole over r tidal cubed. So this goes as m black hole over m black hole to the 1/3. Yeah, I want to, wait, let me do this differently. In order for the disruption to occur, we want the tidal radius to be outside the black hole's horizon, or more specifically, the closest distance at which parabolic orbit won't plunge the black hole without being disrupted. Essentially, the tides need to be stronger outside the horizon of the black hole. So turns out that there is a maximal mass of the black hole for which disruption could occur. Okay, so essentially we want the tidal radius to be outside. I want to write here the gravitational radius of the black hole, maybe times some factor, and this factor depends on, say, the black hole spin, because that sets how close can I approach a black hole without plunging into it. For a Schwarzschild black hole, this A is 8. It's not going to matter that much. And as you can see, this goes like the black hole mass. This goes like the black hole mass to the 1/3. So as I increase the black hole mass, at some point, this will become bigger than this. So let's find what is the black hole mass for which this criterion is satisfied. So we can solve it for the black hole mass over the mass of the star. So let's see. Yeah. So I'm just going to express it like this. I just moved this r star over there. And now let's move this one over here. So we have m black hole over m star to the 2/3. It's to be smaller than this ratio g m star over r star. Yeah, this is going to be r star c squared minus 1. So we see that the mass ratio of the black hole to the mass of the star needs to be smaller than g or c over the escape velocity of the star. So the escape velocity of the star is g m star over r star, square root of that, to the power of 3. So I took the square root, raise it to the power of 3/2, maybe with this a to the minus 3/2. So essentially, if we think about a main sequence star, what is the escape velocity from a main sequence star relative to the speed of light, more or less? Okay, so this is useful to remember. This is roughly 10 to the -3 or so. And this is probably the same for all, well, it's generally uniform across the range of main sequence stars because the mass and the radius go more or less linearly with each other. So that means that the maximal black hole mass that is capable of disrupting a sun-like star is roughly 10 to the 8 solar masses. Question?
I think I answered. That's the escape velocity. That's our black hole, right?
The escape velocity, no, the escape velocity from the surface of the star.
Oh, okay. Thank you.
Yeah. So I just did this algebra and then I ended up with this ratio GM star over R star over C squared. So it's easy to express it in terms of escape velocity and the speed of light. So this is roughly 10 to the 9. With this A, you lose 1 order of magnitude and you get this result. This is known as the Hills mass. And in fact, if you look at from observations, you look at the rate of TDEs as a function of black hole mass. This was demonstrated a couple of times, but now we have more observations, so this has become even more and more convincing. So if you look at the rate as a function of the black hole mass, it's roughly uniform as you go up to masses of roughly 10 to the 8 solar masses, and then there's a decline. Why isn't it a sharp cutoff? Why there's strictly no TDEs above exactly 10 to the 8 solar masses?
Spinning black holes.
Yeah, there's black hole spin. What else? Well, okay, maybe the whole treatment should be done more carefully with GR, but I mean, the basic process is the same, where this is kind of equivalent to saying black hole spin, but yes.
If you have like a supergiant, then the escape is smaller, so that's bigger.
Right. So I was arguing that this is constant for main sequence stars, but this is not exactly constant. And if you go to slightly more massive and puffier stars, then they could be disrupted by slightly more massive black holes, but they are rare. So these effects add up not to contributing much more to the rate. And actually we see this fall. So this was shown in a couple of papers. I'm not sure about the most recent one is maybe Yuhan Yao. Yeah.
Is that related to Brian's question about partial disruptions?
I'm not sure what was Brian's question.
Well,
because he,
Well, just that if you not beta of 1, is that?
this will also add some more kind of spread or dispersion to these statements.
I mean, yeah, basically, beta 1 is the only thing that's allowed when you have a range of allowed penetration from sort of 1 to up to whatever maximum is set by the black hole.
So we'll get to that later, but we'll see that commonly TDs tend to happen when the tidal radius and the pericenter distance are comparable. You don't get a lot of disruptions that are highly penetrating, or at least
One quick
typically not.
request. Please use the microphone and ask your.
Okay,
Sorry, can I add one more thing?
yes,
We can't measure black hole masses very well.
that's true. Definitely not at the low mass end. Here, okay, maybe there's some galaxy scaling relations, but yeah. But you do see some fall off up to our uncertainties about black hole mass. And just to give this, we'll get to that later, but the rate per galaxy of TDEs is roughly 1 in 10 to the 4 years galaxy. And we'll see at least a simple explanation to that later on. Okay, maybe just to add one more thing, you can ask, okay, what about, so we talked about main sequence stars, what about, say, a white dwarf or other objects? Could they be disrupted? So going back to this criterion, if we think about 1 solar mass white dwarf, then what would be its escape speed? from the surface relative to the speed of light? Do you remember? This is actually, yeah, you can remind yourself that for a white dwarf, let's write this here, white dwarf disruption. So V escape of a white dwarf relative to the speed of light, if we are talking about, say, a mass that is close-ish to the Chandrasekhar mass, this turns out to be square root of the ratio of the electron mass to the proton mass. This has to do with the fact that near these masses, electrons at the center of the white dwarf are near relativistic. So then when you think about the typical energy of a particle at the center, it's roughly MEC squared, but what sets gravity is MP. So then you equate the two and you get this ratio. So this is roughly 10 to the minus 2 or so. So you find from this that in order to disrupt a white dwarf, you need a relatively low mass black hole. Black hole of, say, 10 to the 4, 10 to the 5 solar masses. We're not sure how common these are. This is kind of in the range of IMBHs, but there have been some events that have been interpreted as a white dwarf being disrupted by a black hole, but this is clearly not the majority from this argument. Okay. Clearly, okay, in order to disrupt a neutron star, what would you need? Okay, again, going with this logic, right? The neutron star escape speed is almost c, so you can only disrupt it by a relatively low mass stellar mass black hole, if at all. So this is kind of the related to the question of neutron star black hole mergers and whether they produce some EM counterparts or do they get swallowed whole. Yes.
When you say like disrupt a neutron star by a black hole or like a merger, like is there like a conceptual difference between the two?
Between
like a merger of neutron star and black hole and like this tidal disruption of neutron star by a black hole?
Not really. So in both cases, what determines whether the neutron star gets destroyed, even if it's in a merger on a quasi-circular orbit or a parabolic orbit, in both cases you compare tidal gravity to the self-gravity of the star. There may be some order unity differences, some prefactors that go to the calculation with the parabolic orbit and the circular orbit, but essentially in both cases you're comparing the same two things, the same physics.
So the tidal ellipse is the same, but what happens is different. So if it comes on a parabolic orbit, it will be third apart at the same distance, but the fragments of the star will go far away. In a merger, you start on a circular orbit, so it gets destroyed, but it's sitting very close to the black hole.
Yeah, we may discuss, if we have time, we may discuss this scenario in the context of a star around the supermassive black hole towards the end, but yeah, what Ram was saying is right. The difference is what is the total binding energy of the neutron star, or the orbital energy of the neutron star. Okay, so next thing we'll discuss is the energy spread. So initially we were saying that the star is coming on a parabolic orbit. Parabolic orbit has 0 orbital energy. But after the disruption, some parts of there's some exchange of energy between different parts of the star. And it turns out that the disrupted material has some spread in energy that is wider than what it initially had. Okay, so initially, the orbital energy is 0. This total energy remains after the disruption. But the difference is that if we look at the distribution, say dm dE is a function of energy, so how much mass is stored in each bin of orbital energy, and initially all the star essentially has this 0 orbital energy, all the different fluid parcels. But as it approaches the black hole, so now we'll visit what happens when we approach the tidal radius. This. So roughly when we are at the tidal radius, the star, which was initially circular, now has this order unity tidal bulge. It's deformed to a size, or the deformation is comparable to its own size. And that means that that now different parts of the star are now in different areas of the gravitational potential from the black hole. So now it is perhaps distorted to twice its initial size. So there are different ways to think about what exactly happens here and how much energy do these different parts get. One way is to think about how once this big bulge in the star develops, it now feels torques from the black hole, right? Different parts are torqued differently. And in fact, the disruption is kind of equivalent to the star being spun up to its breakup velocity, or its breakup spin. This means that while the entire star is moving with some Keplerian velocity, there's going to be a difference in velocities where, due to this spin, where this part is going to be spun up to roughly the escape speed from the star in this direction, and this is going to be spun up in that direction. So if we think about differences in energy between these different parts, then we have something like, we want to add these different velocity vectors. During the disruption, they change angles. So in general, they're not necessarily parallel like I've shown here. So you get something like VK squared plus or minus VK times the escape star. So we see that with the plus or minus, this part versus this part, they have a difference in orbital energy. So this is per unit mass. Of roughly VK times V escape star. Maybe a factor of 2, but as I said, we're not keeping factors of 2 here. This is square root of G, let's do this in the right order, M black hole over the tidal radius. So that's roughly the Keplerian speed as we approach the tidal radius. And the escape speed from the star, we already wrote it, Gm star over R star. So this comes out to be roughly Gm star over R star, which is the binding energy of the initial binding energy of the star per unit mass, times, so let's see. Yeah, we have here M black hole over M star to the 1/2 times R star over R tidal to the 1/2. And if we remember that the tidal radius is bigger than the size of the star by M over M to the 1/3, this all comes out to be M black hole over M star the 1/3. Okay, so initially, all these fluid parcels had more or less the same orbital energy, 0, or with a very small spread around it. But after the star gets spread apart or tidally distorted, then we develop some energy spread or difference between the binding energy of different parts that is much bigger than the initial binding energy per unit mass of the star itself. Okay, this is again a factor of 100 bigger. Equivalently, you can write it in terms of the binding energy, or yeah, the energy that a particle on a circular orbit on the tidal radius would have had. And this is going to be smaller than that by m star over m black hole, the 2/3. Any questions so far? I'll show in a minute another conceptual way to think about this. Okay, another equivalent way of thinking about it, which also gives the right result, is to say the following. Let's draw this here. So if we think about what happens to the star after it enters the tidal radius, then we know that at this point, tides exceed the star's self-gravity, which means you're kind of lifting the potential or the pressure gradient within the star. And we have these two halves of the star. We have this half, and they're now going to attract one another with gravity that is roughly gm star over r star squared, again, per unit mass. This is going to be the gravitational attraction between these two disintegrated parts of the star. Yeah.
Just going back to this, so
Yes.
like if I had a MESA model,
Yeah.
can I just replace m star with m of r and r star with little r to understand how the energy is maybe distributed? Or is this too cartoon to like actually, you know what I mean?
I'm not sure. You
Like-
mean a MESA model that will?
So, oh, right, so you have that distribution first, which is a delta function initially. And so if we wanted to draw a dotted line there for how the energy is distributed across the star, this expression depends on m star and r star. But I mean, could I just replace that with m of r and little r in the star? Or is it that's way too kludgy?
This is quite a cartoon picture.
Okay.
And you can do the hydro simulation of taking a star, passing it through the tidal radius and see what happens. And you'll get the right result. I mean, this kind of agrees with the simulations, maybe after some normalization that needs to be accounted for. But the point is, and then I'll finish this other way of thinking about it. So after the disruption, you get a spread in energy that is more or less this delta E orb. And it might have some complicated shape. Maybe it's something like this. But the point is that more or less we have a solar mass, or the mass of the star spread across this energy spread. So this is going to be m star over this delta E orb. And although the details might be more complicated and will depend on the structure of the star and so on, you more or less get something that looks like this. It has this typical spread and this typical height. And we'll show later that, in fact, in order to determine some of the properties of the transient and so on, you don't really care about the detailed structure of this distribution. Yeah.
So, I mean, it's been a long time since I've looked at the Reese paper, but
Yeah.
I feel like whenever people quote the old papers, they just assume that like each bin, like
Yeah.
delta M over delta E is flat.
Yeah, we'll We'll get to that
Maybe
soon,
talk about
but it
that,
actually
okay.
turns out that it doesn't really matter all that
Okay,
much.
okay.
At late times, you're only going to care about the distribution around energy of 0, but we'll see why that's the case soon. Okay, so just to finish this point here, so if we think about these two parts of the star now pulling each other, then they're going to perform some work on the stellar material. And this work can be estimated as this force, right, times some distance. What is the distance over which we need to think about the process that gives these different parts of the star different energy? Any ideas? The black hole is here. I mean, there is one scale that we talked about repeatedly. It's essentially the pericenter passage length, which is comparable to the tidal radius. So essentially, multiply that by the tidal radius. And then just to see that you get the same result. So this is going to be G m star over r star. Right? Again, this is r star times the mass ratio to the 1/3. You got this m black hole over m star 1/3, which is what we got here. Okay? Any questions about the energy spread? We'll soon discuss what can we learn from it and what's the point in even discussing it, but just to make sure that we're on the same page. Okay, there are no questions about this calculation, then let's see what are the implications. So initially, all the material was on this parabolic orbit, but now some material has positive energy, which means that it's unbound from the system, it will be ejected. And some material is bound. If indeed we started with 0 orbital energy, then this is going to be exactly half and half, because the total energy is still conserved to be 0. So we'll have unbound material. This is going to be roughly half the mass of the star. It will have, right, so maybe this is delta E orb over 2. This is minus delta E orb over 2. But again, without caring too much about the details of this distribution, roughly, right, the mass up to here, say half of this maximal energy, here you're going to have a considerable fraction of the stellar mass, or the half stellar mass that is unbound. And it will have velocities that are comparable to this delta E orb, square root of that. So the velocity at infinity of this unbound material is going to be roughly square root of delta E orb. Is that clear? So if we plug in that result, this is going to be, this one is going to be useful. So I'm going to square root GM star over R star. What is that? We mentioned this before. This is the escape speed of the star. What am I missing? M black hole over M star to the what power? 2/3. So I'm going to take the square root of this 1/3, so 1/6. This ratio of 1,000,000 is again useful because then this turns out to be 10. So material that gets ejected from the system is traveling at speeds that are 10 times the escape speed of the star. So maybe 10 to the -2 C or so. This has potentially some interesting consequences. Maybe this unbound material interacts with some ambient medium. Maybe it produces some afterglow. these are ideas that have been explored and are still being studied to understand some aspects of the observations. Okay, that's the unbound material. It gets more interesting with the bound material. Okay, so the bound material comes at different levels of boundness. So the most bound material has binding energies that are roughly negative delta orb, maybe delta orb over 2. But there's a distribution of binding energies that goes all the way to 0. So there's going to be some material that is very marginally bound. What does this mean? So if we think about the disruption process, maybe I'll use this plot here. I'm going to erase this. This is just reproducing the result that we've shown. Right, so this material, this side of the star is going to be more bound. This is the unbound stuff. If we think about, say, this part, which just for the purpose of illustration is going to be the most bound material, it is going to be falling back to the black hole on some eccentric orbit. How do I know that it is eccentric? So what do I need to compare to see that the most bound material, that one that has negative delta E orb, is bound? I need to compare it to the orbital energy of a particle on a circular orbit and convince myself that it's much less. I can see this here, right? So this is the energy of particle on circular orbit at RT. And this is a factor of how much? For this factor of 1,000,000. 10 to the minus 6 to the 2/3. 10 to the minus 4. Oh, is this right? I think I made a mistake here. This should have been 1/3. Okay, so this is going to be a factor of 100 less bound than a particle on a circular orbit here. So that means that it will have an eccentricity of roughly m star over m black hole to the 1/3. So this is an eccentricity of 0.99 or 1 minus eccentricity of 0.01. Okay, so the most bound material is gonna follow now an orbit that is highly eccentric with a pericenter roughly RT, an apocenter that is 100 times bigger. Right, just to remind you, the orbital energy is minus G m black hole over 2a, again, orbital energy per unit mass. So this tells me what is the semi-major axis. And the eccentricity is the pericenter distance over the semi-major axis. Okay, so we'll have this very bound material, or most bound material, but it is still going to go very far before it comes back. But as I go deeper and deeper in the star, this material is only marginally bound, which means it's going to follow an even more eccentric orbit until it comes back. So it will come back at a later time. What I can do from all of this is estimate the rate at which material from the bound star returns towards the pericenter, towards the black hole. possibly feeding it and generating emission.
But won't you have some matter that is on a circular orbit?
No. So even the most bound material, right, in order to be on a circular orbit, I need to have a very negative orbital energy. But the most negative I can get from this heuristic argument that we made is capped to some value. Maybe, you know, this calculation is perhaps off by a factor of 2, so maybe it's not here, it's here, but still, you're not going to get, you have a factor of 100 or 1/100 to fight against. Okay, is this clear? Okay, so we want to describe how these different parcels of fluids return to the black hole. So to do that, we will try to assign a time scale or an orbital period to each of these different values or different parts of the star that have different values of binding energy. So let's start with the most bound material. What is going to be the fallback time, or the time over which it completes one orbit before returning to where it was, where the star was disrupted initially? So let's do that. So the orbital period, let's call this T fallback. So this will refer to the most bound debris. So roughly half of the star, or not necessarily half, but maybe a quarter, half of the star will have energies that are comparable to this value. So this will be the orbital period for some semi-major axis. Let's call it most bound. So this is going to be the semi-major axis of this most bound material is going to be RT over 1 minus E. So as we said, this factor of 100 bigger than the tidal radius. It's 2 pi times square root the most bound semi-major axis divided by G M black hole. And we can do the following. So this is going to be, I'm just going to write down what we have there. So it's RT cubed over G M black hole times this is this 1/3 to the 3rd power. But we already mentioned this. What is this without the m over m here? Previously, when we talked about an orbital period, so that's the orbital period at the tidal radius, right? And what is it? We mentioned this curious identity between the orbital period at the tidal radius and the dynamical time of the star. So this is more or less the dynamical time of the star times the ratio of the black hole mass over the mass of the star to the 1/2. Maybe there is a factor of pi here that I'm neglecting. So m over m to the 1/2 is 10 to the 3. If you do include the right prefactors, it turns out to be for a 10 to the 6 solar mass black hole and a sun-like star, this is roughly a month. Okay, so this is the time scale over which parts of the star that are most bound will fall back to the black hole. This is true for, as I said, a good fraction of the star, depending on how flat this distribution is. But if it's not doing something crazy, then some comparable fraction comparable to the entire mass of the star is going to return on this time scale to the black hole. Okay, what's going to happen to less bound material? It will also return, but on longer time scales. How much longer? This depends on how much their binding energy is less negative than that of the most bound material. Let's do this here. So I want to assign every orbital energy some orbital period. And this is going to be done in the following way. What I'm actually interested in is the rate at which material falls back to the black hole. So we know that over this time, over the fallback time, roughly the mass of the star up to some correction factor returns. So we know that there's going to be some maximal fallback rate, which is going to be the mass of the star over this T fallback. But at later times, you're going to have less and less mass returning on these more eccentric, less bound orbits.
Right, this
Yeah.
is the time to return to pericenter.
Yes.
And in fact, you're calling it m dot because
It's m dot in the sense that this is the rate at which material returns to pericenter. I'm not necessarily saying this is going to be accretion rate onto the black hole, but this goes to a discussion we'll have later. So I'm going to do the following. The m dot from this bound material onto the black hole is going to be, it's dm dt. And we're going to use the chain rule and use this distribution of masses over different energies times the time at which each of these energies corresponds to some orbital period. So instead of t here, I'm going to replace it with the orbital period matter with binding energy E, orbital energy E. So this is going to be dm dE evaluated at some energy times. So let's do this. So we wrote here the orbital energy. Let's convert that into dE dP. Okay. So we have Gm over A. I'm going to neglect factors of dimensionless factors, but you can write down the orbital period as a function of A, or vice versa. The semi-major axis as a function of P as G m black hole P squared to the 1/3. This goes as P to the 2/3. And then we have here G m black hole over P to the 2/3. And if we take the derivative, dE orb dP, right? So we have here E goes as P to the minus 2/3. So taking one derivative, we end up with what? Taking the derivative of P to the minus 2/3. Minus 5/3. That's right. So here we'll have, I'm going to write the right expression, including the physical quantities. Okay, so this is going to be the fallback rate. And the key point here is that the fallback rate goes as T to the minus 5/3. This is true at late times, at times that are much longer than this initial fallback time, which we estimated here. So what's the what's the idea here? So as I wait longer and longer, now I'm seeing material that has longer and longer semi-major axis, longer and longer orbital periods. It means that we're now sampling stuff with less negative orbital energy. And at very late times, what I care about is the distribution, the MDE, around 0. So essentially, at late times, this E goes to 0 from the negative side, and we're seeing this marginally bound material. This T to the minus 5/3 is kind of a key feature of TDEs, and in fact, not necessarily for super well understood reasons, but sometimes TDE light curves, and we'll talk about the emission sources later, seem to trace something that falls off in terms of the luminosity, falls off as T to the minus 5/3 or some power law, and sometimes this is argued as a sign of this is actually a TDE, what we're seeing. This is a famous result from about 30 years ago. Any questions about this? Okay. So all we discussed so far is the rate at which material returns to pericenter. What it does there is now less clear. So we talked about the things that are kind of pretty well understood about TDs, and now it becomes a bit murkier.
Itai,
Yeah.
is there an intuitive way to understand why the MDE is similar for that most bound stuff so that there isn't another time dependence besides the T to the minus 5/3?
Right. So there is going to be some time dependence in the sense that you're going to probe different parts of this, the MDE. Right. I just erased it. Let's say it does something weird like this. Half of the mass is unbound, half of the mass is bound. But as you wait longer and longer, you approach closer and closer to what happens exactly at 0. And regardless of the shape of this function, it's going to have some value over here. And this value is what determines the fallback rate, how much mass per unit energy is there as you go to these smaller and smaller values of E. So essentially, it's very unlikely that you'll get some additional time dependence unless the function does something very weird. For some reason, it knows that it needs to deplete the amount of mass around 0 energy. It is going to be true for, maybe in partial TDs, you're going to get something slightly different.
I guess if we just think about like what is the spread in energy once the distance between neighboring shells gets really small, right? Like the binding energy goes as 1/r. So that like the energy varies sort of linearly with that little delta R.
You're talking about, but you're thinking about hydrostatically balanced star, right?
Well, I mean, you just wrote the difference, right? Yes. There's a spread in the force across from,
there's going to be some force gradient, and maybe you can,
but that analytically very strongly with this little delta R from the center. So maybe you can imagine that.
It's a bit more complicated because, right, you also have, it's not just pure gravity, you will have some hydro effects that also take place here. And actually, to get the right shape of this, you do need to run a simulation. But the point is that it doesn't really matter what is going to be the exact shape, as long as it's going to have some typical width and typical height, even if it's uniform or not. And then, this result about T to the minus 5/3 just reflects the fact that there is some value of the function over there.
Okay. Oh, because it's just the limit of that function. As
Yeah,
you go to
as you
zero.
go to very long times, you go to less and less negative energies,
Yeah.
closer to zero, and that determines how much mass is going to fall back at later times. At each time interval, there's some orbital energy associated with it, close to zero, and that's what you're going to see. Okay, so if we were to plot this last result, m dot as a function of t. So let's say the disruption happened here. Nothing is going to return until this t fallback, the time of the most bound debris. And it's going to rise on some typical timescale, maybe twice that timescale. And then at late times, it's going to fall off t to the minus 5/3. This maximum here being roughly m star over t fallback. It's true that the details of this function, how does it look around its minimal edge, right? This is delta E orb. That will determine the details of this rise. Okay, so what happens to material that falls back? So one important effect that was appreciated is that, in fact, these streams that fall back, this stream of bound material that return, they also undergo some upsidal GR precession. So we mentioned before that our tidal over the gravitational radius of the black hole is roughly 50 or so. So it means that this problem is not super relativistic, but some corrections are going to play a role. So this implies that, let's draw this separately. This implies that if we have this tidal radius, there is the black hole, and we have some material that falls back at some point, it is going to upsidally precess and not actually remain on this nice ellipse from the disruption. This ellipse is going to precess. So every orbital period, it's going to attain some angle. This angle can be estimated as roughly 3 pi Rg over Rt. So for these values that we talk about, this is of order 10 degrees with every pericenter passage. So that means that potentially these streams of falling back material will self-intersect. Maybe they'll collide far from the pericenter, and you can do the geometry and estimate where exactly this happens. So some people think that these collisions between streams of returning material that pass quietly through pericenter, because maybe there's nothing special that happens there, maybe then they eventually collide and thermalize far from the black hole. That is one possible mechanism for producing emission from these processes. Which brings me to the next point. So possible sources of emission. This is going to be quite crude, and maybe later on after Suvi will review the observations, we can talk a bit more about this. So one of the initial ideas that people had is that if for some reason, due to the complicated and messy interaction between these streams, material can be accreted rapidly onto the black hole, maybe these collisions over here, maybe because there are shocks that develop as the material returns to pericenter and gets tidally compressed. This is called the nozzle shock. If accretion could occur rapidly, then maybe the rate at which matter falls back to the black hole could set the accretion rate onto it. And then if this accretion can lead to radiation, then perhaps these sort of events could just produce bright emission from the accretion of this falling back material. That was one of the earlier ideas that have been discussed. Now, there are some difficulties with this picture because it's not quite clear how efficiently and how rapidly can this material actually circularize and form an accretion disk and feed the black hole. So I would say still a question of debate, what exactly happens shortly after the disruption when material starts to return. Another possibility which I alluded to are shocks. I'll explain close to RT or close to these semi-major axes. So maybe you do promptly form some accretion disk around the black hole, and maybe this material that falls back then collides with the black hole, produces shocks that can then radiate. So again, there are different ideas and models that invoke different mechanisms. So maybe you have shocks close to the black hole with accretion flow that you already developed. Maybe all of these shocks are far from the black hole from this kind of more extended material. You should note that these streams, as we estimated, are highly eccentric. So the material from the disrupted star goes very far away from the black hole before it returns. So it's feasible to think that a lot of this material actually remains far from the black hole, and maybe a lot of the action is actually not happening initially close to the black hole, but far away. Maybe after this material collides and self-intersects, it can fall back and feed the black hole and produce radiation. So another idea, also Brian has worked on this, is this idea that perhaps what produces the emission in these TDs is some cooling envelope. And the idea is that, okay, there's some messy interaction of streams and so on, but the entire bound material has energy that is very small relative to the binding energy close to the black hole. So maybe all of this system just gets enshrouded by some envelope with distances that are, say, 100 times the tidal radius. So this goes back to this m over m to the 1/3 times RT. And this hot envelope slowly contracts and radiates. So that is another possible emission mechanism. If indeed a lot of material gets fed onto the black hole, and if the magnetic field configuration is favorable, then maybe these systems could also produce jets, relativistic jets. And we have some reasons to believe that this occurs occasionally in some TDs, but we're not sure why it happens rarely or with the fraction that we see. I mentioned before these outflows, either of this unbound material, so half of the star that gets unbound and interacts with the environment, maybe the accretion onto the black hole produces not just jets, but it could also produce super Eddington winds and outflows, and these outflows could produce some emission. Maybe this is related to the radio observations that we have of TDs. And there are more exotic ideas, like if the star passes around pericenter, the tidal forces, turns out they compress the star. So aside from stretching it in the plane, they also compress it vertically to the plane. So that could, in principle, increase the temperature within the core of the star and maybe ignite nuclear burning. So this is an idea that has been explored, also perhaps relevant to the white dwarf case. So there are various ideas that have been invoked in this, as you see, complicated problem to how one could produce radiation, and the observations seem to to lead us into thinking that possibly all of these components are present to some extent, and we'll hear more about the diversity of observations in the next talk. I will mention another quantitative result, which is if you look at this fallback rate, it turns out, so if you plug in typical numbers, it turns out that this ratio, the peak fallback rate, is going to exceed the Eddington accretion rate of the black hole by a factor of 100 or so. So this is roughly 10 to the 2 m dot Eddington. And it's not clear that even if you do form an accretion disk and so on, it's very unlikely that all of this mass actually ends up being fed to the black hole and re-emitted as radiation. So maybe some of this material just falls quietly into the black hole without radiating at some constant efficiency. Maybe a lot of this material gets ejected as outflows. And it turns out that the fallback remains super Eddington for quite some time. So you can estimate it with this T to the minus 5/3. So essentially, I mean, just to say this in words, if we want to estimate at what time will the fallback rate go back to Eddington, so let's say it's over here. So you simply have to take this factor of 100 and raise it to the power of 3/5 to get where this intersects that, and multiply it by T fallback. So let's call it T Eddington. So the duration over which the fallback rate exceeds Eddington. So that is going to be roughly T fallback times this ratio, and to the 2 T/5. And this turns out to be roughly, very roughly, a year or years. So in terms of our expectations of what you see here, it's clear that maybe at late times we're seeing something quite different from all the exciting hydrodynamics that takes place at early times. And indeed, it seems like late times observations of TDEs show something that is well explained by an accretion disk feeding the black hole. So I'll just mention this briefly. You probably will hear more about that. We usually see something that looks like, I'm just gonna draw this schematically. So this is the black hole, and there's some accretion disk around it that is feeding the black hole at some m dot disk, which is sub-Eddington. And you can actually demonstrate that so it produces X-rays that come from the inner part of the disk. And it also produces an optical and UV emission that comes from the Rayleigh-Jeans tail of material that is at the outer skirts of the disk that is slowly spreading. And there's this nice result that actually this spreading disk, if it maintains its angular momentum, would produce an optical UV plateau, or something that is close to a plateau. Optical UV plateau. Hard word. Yeah, so this is sometimes seen in late time observations. Okay, any questions so far? Yes.
So what causes the precession of the streams?
It's GR precession. So this result here, it's due to the fact that pericenter is far, but not too far from the black hole itself. And you can actually see, this is related to some things we talked about earlier. So when you move to more massive black holes, so close to this limit of 10 to the 8, and this precession becomes even more substantial. So TDEs of a given star around black hole masses that are bigger than 10 to the 6, approaching this 10 to the 8, they become more and more relativistic in a sense. So the velocity, for instance, of the star as it approaches the tidal radius becomes closer and closer to C. And then also, yeah, this precession, for instance, would be more important. Maybe if there's black hole spin, the trajectory of these streams will also undergo nodal precession. So it's not even clear that these streams could then collide after one orbit, because right then the fan of streams will kind of precess nodally. So you might have to wait longer until they first collide. So people have been thinking and working on these questions. More questions, yes.
So if you have a non-spinning black hole, then the
Precession
is just always in the plane, but if you have some spin, then you also have a vertical.
Right.
Swoop. Okay.
Now, nodal precession is generally weaker than apsidal precession. So if and these streams have some width. So if the disruption happens far enough from the black hole, even if it's spinning, then maybe these streams could collide. Yeah. Okay, I see I have. Yeah.
If this picture is correct and the streams are colliding or producing the emissions, then right, the collision point is going to be if you assumed that the Perry was the tidal radius of what we call beta 1.
Yes.
Right, the collision radius will be a very sensitive function of the black hole mass.
Yes.
Right, because as you go for lower mass black holes, you're disrupting far from the black hole, so it's very gradual precession, and it would collide far away. Right. And as they go up in mass, they should collide closer with a higher power.
That's right.
So I think this collision picture would predict very strong dependence of the emission.
Yes.
On the black hole mass.
Right. So I mean, I should have mentioned in all of these scenarios, probably some level of reprocessing is also important. So if you do end up with this kind of messy cloud of material, then perhaps it reprocesses the emission either from the accretion onto the black hole, or these shocks and their emission could also be reprocessed. Okay, I see I only have a couple of minutes left. I can briefly say something about rates of TDs, but maybe I won't have time for that. Or I can say something about some other related phenomena. Do you have preference? Yes.
How do you get a cooling envelope? Like, how do you get any momentum going out of the plane? Or something like, it seems like everything is very much
in the plane. Yeah, so we just mentioned nodal precession as one form of kind of creating this spread. And if you do, perhaps you do initially have collisions that are in the plane, but right after you collided these two streams, you thermalize, and then you also get some sideways motion. So maybe not immediately, but one could in principle invoke these collisions and all of this messy picture to eventually form something that is quasi-spherical. I don't know if Brian has some.
Well, I have two things. One is observationally, photosphere radii are huge. They have to be a large covering fraction. So you could say observationally, we see that there's something that's covering a large part of the spherical surface. I would say also that these are very low angular momentum streams. So it's not particularly like if you do try to form some structure, it isn't really rotationally supported. It's rotating very slowly because of small angular momentum. So it doesn't necessarily want to form something that's very disk-like if you do thermalize it once. So
yeah,
we can talk more.
Maybe just some numbers to bear in mind. This will also be relevant for the observation. So if you invoke some volumetric luminosity that is of order Eddington, we said fallback rates of Eddington only appear after a year, but maybe all of these messy processes are somehow Eddington limited. So yeah, if the photosphere radius, so where the emission is coming from, is roughly 10 to the 15 centimeters, which is roughly 100 times the tidal radius, which is what we said to be the semi-major axis of the bound streams, then you can infer temperatures that are of order 1 eV, or 10 to the 4 Kelvin. So this is kind of a way where how we think that this explains the optical emission that we see in TDEs. And alternatively, sometimes we do see X-rays, which we think are related to accretion onto the black hole. So again, if you think about, take the same luminosity of Eddington, but now say that it arises from accretion onto the black hole. So you equate the accretion power at the ISCO, some m dot, and you equate that to some black body emission from the ISCO. Then you'll find black hole temperatures that are of order 100 electron volts, so X-rays. And this is going to be optical UV. Okay, so I see we did this and this. We didn't talk about rates. We didn't talk about related phenomena. Maybe there's time for a couple more questions. Usually, questions, okay?
Questions.
You could say a few words about related phenomena.
We had a question. Was it?
Well, there
Yes.
is a question.
Oh, okay.
Okay, related phenomena. Okay, so there are a lot of related phenomena, but a couple of things I've mentioned here. So in the last few years, we're seeing more and more transients that happen in galactic nuclei that repeat. So while a TDE kind of canonically, we think of it as a one-off event. The star passes, gets destroyed, produces this messy picture that radiates, and that's it. So one development is that we are finding things that could be interpreted as repeating TDEs. So the basic picture is that if a star grazes the tidal radius but doesn't penetrate it deeply, then maybe only its outer parts will be stripped and then produce all of this interesting phenomena. And then the star, if it remains on a bound orbit around the black hole, it will eventually come back to another visit, another pericenter passage, which will produce another TDE-like flare. So we're trying to understand under what conditions can this happen and how finely tuned does this have to be? Because at least at face value, it sounds like this would only happen rarely if you want to say disrupt just a small fraction, say 1% of the star of the mass of the mass of the star. But we are seeing these, so that's one interesting front. And the other has to do with QPEs. So this is a new class of repeating X-ray flares that we see from galactic nuclei. So they look something like this. This is the X-ray flux luminosity as a function of time. So there's some quiescent level that we are seeing in these galactic nuclei. And then there's some flare. And then a few hours later, there's another flare, and they repeat with timescales ranging from hours to days. So there are a lot of different ideas around these sources, but one possibility that we explored is the idea that what we are seeing is actually a TDE disk like I plotted here. But there is also a star, unrelated star that is unrelated to the TDE that happens to orbit the supermassive black hole and collides with the disk twice per orbit. And these collisions could then produce these X-ray flares. So this is interesting because it also tells us something about the accretion flow around black holes. It tells us if indeed this is the right interpretation. It tells us that there are stars that are quite close to supermassive black holes and centers of galaxies. So we initially made, so this is Brian and I, we worked on this, and we made a prediction that this scenario could happen in some fraction of TDEs. And indeed, about a year ago, there was an observation of a TDE that was followed up a couple of years after it happened, in the phase where what we're supposed to see is just this bare disk feeding the black hole. And then all of a sudden, with sufficiently long X-ray observations, we're seeing these repeating X-ray flares. So possibly this picture is interesting to continue and explore. But there are other ideas as well, explaining what QPs are. This is just one possibility. Okay.
Right. Any final questions? Yeah. No.
But there's no question. It's just basic point, which I think that community largely is sort of hasn't fully come to appreciate. But basically going from this stage to this stage, we see this at the end. This is the initial condition that I think Itai motivated very well. There's a release of energy. If you're going to take matter that's in a weakly bound orbit, put it into a disk near the tidal radius, there's a release of energy, and we have to see that energy come out, unless it somehow gets sucked into the black hole, which is unlikely. And so I think, this is one of the interests. This, you can call it a cooling envelope. There could be a lot of messy processes, but I think there's sort of a, at late times we see these disks, and so I think there has to be some explanation. And that's probably somehow is related to the early flares we see. But as Itai said, it's messy.
Right, thank you. Okay, let's thank Itai. All right, we are ready to get started with our second session for the day. So our second session will be on the observed variety of tidal disruption events and how they emerge in all kinds of surveys, and hopefully with an insight on what LSST brings to us. This will be a visiting lecturer, Suvi Gezari. Suvi got her undergraduate degree at Brown, followed by her PhD jointly between first UCLA, then Columbia, and then was a postdoc at Caltech and Johns Hopkins. Mm-hmm. Yes, Johns Hopkins, and then became professor at Maryland, then moved to Space Telescope and is now moving back to Maryland. Okay, I got it all. Yes. Suvi works on a wide variety of energetic transients in the centers of galaxies, and today we'll be telling us about the tidal disruption events.
Great. Thank you so much, Kishale. It's wonderful to be back in New York City, where I did get my PhD. So Itai really set us up nicely with some of the beautiful, well-understood theory on tidal disruption events. I'm going to show you a little bit more of the messy reality of what we've been observing. But in fact, this is a really exciting and dynamic field. We're learning new things every day. And so it's valuable area for you guys to learn more about. And I think Ruben is really going to be transformative for this field. So there's lots to cover, and I can sort of go at different paces, but we can see sort of which areas you guys are most interested in. But I will be focusing a lot on what we've learned from optical ground-based wide area sky surveys that have been discovering tidal disruption events in the nuclei of galaxies. And shown here is an example of the type of imaging we do with the Zwicky transient facility, which is on the Palomar Observatory. And you can see where we're taking images of the night sky and then using difference imaging to find things that are changing and flaring and bona fide transients. And we're specifically honing in on what's going on in the nuclei of galaxies. So we heard a lot of theory this morning, and in fact, one of the seminal theoretical papers on that sort of set the stage for understanding the expectations for tidal disruption events is this Rees article in 1988, which really beautifully showed a lot of the arguments that Itai described to us, and even speculated on the presence of a supermassive black hole in our own galactic center, which of course we now know exists from various pieces of evidence. But while this really started as a theoretical concept, I'm here to show you that it is now definitely an observational reality. So we are observing tidal disruption events across the electromagnetic spectrum. So as we heard, TDEs are specifically sensitive to these lower mass black holes, less than 10 to the 8 solar masses. And this is really an interesting range of black hole masses where we don't have a lot of direct information on these really important scaling relations. For example, we observe from the dynamical studies of black holes in nearby galaxies that there appears to be a tight correlation between the mass of the black hole and, for example, the stellar velocity dispersion of the host galaxy bulge. And so understanding these scaling relations, how massive black holes and their host galaxies likely co-evolve over cosmic time, we really don't have a direct window into these lower mass black holes from dynamics. And so tidal disruption events are a really exciting probe of this regime. And we heard about the theoretical fallback rate of a tidal disruption event. And this is really exciting because in principle, based on this basic theory, the time at which the flare from a tidal disruption event peaks should scale with the black hole mass to the 1/2 power. So these events, not only do they light up black holes lurking in the centers of galaxies that are otherwise dormant, but perhaps we can even use the observations of the light curves to weigh the black holes in their centers. And also, Itai talked a lot about the scalings with black hole mass, but in all of the equations he put on the board, many of them also include the mass and the radius of the star disrupted. And so we can actually, again, probe the true stellar populations in the centers of galaxies that otherwise would be very difficult for us to probe directly. And for example, even such things as the fallback rate. Oh, yes.
Sorry, what was the velocity on the x-axis in that scaling relation you showed?
That was the velocity dispersion of the host galaxy bulge. So it's basically a proxy for the mass of the bulge. It's way outside. We're talking about velocities way outside the influence of the black hole. So it doesn't feel the black hole. It feels this black hole, this stellar mass potential. So Itai derived for us the fallback rate for a main sequence star, which is shown in the middle in blue. But you can see that given what we know about the diversity of the stellar populations in galaxies, you are going to have dramatically different both time scales as well as peak accretion rates relative to the Eddington ratio for the different types of star, with extremes going from white dwarfs, which are extremely dense and compact, to red giants, which are very large and tenuous. And so again, there are potential observational signatures of different types of stars when they get disrupted by the black hole. We also, Itai mentioned this idea of the maximum mass that can disrupt a star outside the event horizon. And this is also really interesting because while main sequence stars have typical upper mass limits of about 10 to the 8 solar masses, these very dense, compact white dwarfs actually can only be disrupted by black holes less than 10 to the 5th solar masses. And so they are, again, a very unique probe of the very low mass black holes, which we call intermediate mass black holes. Itai didn't get a chance to talk about rates, but in general, you can find some basic scaling relations that show you how the tidal disruption event rate scales with the stellar density in the center of the galaxy. And so as you get to higher densities, you get higher tidal disruption event rates, getting to about once every 100,000 years per galaxy. And this is kind of fun because as we're studying the early universe with JWST, we're finding these very compact, dense systems, which potentially could yield very high tidal disruption rates. So again, TDEs are probing sort of nuclear densities in the centers of galaxies, stellar nuclear densities. So we are in an era of large surveys across the electromagnetic spectrum, from the soft X-rays to optical, mid-infrared, radio, including particles like neutrinos. And in the future, we're going to have even more exciting surveys in the UV, as well as, of course, Rubin in the optical and in the infrared with Roman, and of course, gravitational wave surveys. We know now that, in fact, tidal disruption events are multi-wavelength emitters. So I really like this figure, which shows the basic spectral energy distribution of a typical tidal disruption event. And you can see it has multiple components, mostly thermal components, that range from soft X-rays, which Itai argued are what you'd expect from around the ISCO, near the inner radius of accreting material around of the disk. We see bright optical emission, UV and optical emission, again around 10 to the 4 Kelvin, which is, we don't know the exact origin, but seems to be coming from larger radii, maybe associated with the stream-stream collisions that was discussed. We also see delayed brightening in the mid-infrared, which can be interpreted as a dust echo, where ambient dust in the region near the supermassive black hole is illuminated by the UV photons and then re-radiates in the infrared. And we also see late time observations of radio emission, as well as sometimes prompt radio emission from a jet or outflow. And so I show this schematic here showing the various parts of the accretion flow and a tidal disruption event, and it really produces this beautiful variety of signatures. And so depending on which survey you are using, you're going to be picking up on these different components, and I'll be showing you how we do that. So right now we're really in a golden age of wide field optical surveys. I'm going to be talking a lot about results from the Zwicky Transient facility, which has been operating since 2018. But of course, Rubin has already started observing on the sky and is going to be really taking us to the next level of wide and deep optical survey possibilities. So when I first started in this field, we were really excited when we were discovering TDEs at a rate about 2 per year. That got us going. With ZTF, this is sort of increased to tens of TDEs per year, and we're now over 100 secure TDEs in literature. And with Rubin, this is going to be going to thousands of TDEs per year. But it's this slow ramp up and using these various surveys that's been able for us to get these samples where we can really look at the average properties of TDEs. So originally, the first TDE discoveries were made using repeated X-ray data on over wide areas. For example, ROSAT, and this is the XMM SLU survey. And they found that there were large amplitude changes in the X-ray flux in otherwise quiescent galaxies. And you could fit, the few points that you would have from these surveys with a T to the minus 5/3 power law, and argue that this sort of large amplitude X-ray variability really could only be described or attributed to a tidal disruption event. With our optical searches, we are now getting extremely detailed light curves. And these optical surveys like ZTF and PanSTARRS and PTF and Assassin, they were really designed to study supernovae for various reasons, including supernova 1A cosmology. But we've been able to use this high cadence optical data, as well as this powerful technique of difference imaging, to ignore all the supernovae and actually look specifically at transients going on in the centers of galaxies. Now, in the old days, people were scared of the centers of galaxies because of AGN. I'm going to be talking about AGN tomorrow. I studied, my thesis at Columbia was on broadline AGN and their double peak profiles. Back in the day, we thought AGN were interesting. But it turns out that once you are able to identify AGN as well as supernovae, then you can really hone in on this other unique nuclear transient, which we think, in fact, is due to a tidal disruption event going on. And you can see here these beautiful optical light curves and their fit to the basic T to the -5 Hertz power law. And they really look a lot like the predictions for the fallback rate. So this is just showing the diversity of transients that ZTF is discovering all over the sky. Hopefully you guys have looked at the data, and you're going to be using some of the data and the modules, but it's really a fantastic data set to get ready for Rubin. It's much shallower than Rubin, but it has beautiful cadence of 2 days in the GNR band. It's all public. They use the same alert streams that Rubin will use. So it's a great sandbox for training your various projects. Yes.
What are the gaps?
That is the Milky Way. So we can't look too where it's too dense on the sky, right? Isn't that the Milky Way? Yeah.
No, I think they do look, but they don't classify anything over there.
Okay. Yeah. Okay, so we use difference imaging, and we're specifically looking in the centers of galaxies at nuclear transients, but you can't assume that everything you find in the center of a galaxy actually is a tidal disruption event or even an AGN. So I just have to remind everyone that supernovae also explode near the centers of galaxies. And so especially things like type 1A supernovae, which early on can be quite blue, you really have to be careful about filtering them out from other phenomena. So the way we do this is we don't just use the shape of the light curve, but we also use the colors of the light curve, and in particular, how those colors evolve with time. And the most powerful discriminator between a phenomena like tidal disruption events, which are accretion onto a black hole from this fallback of debris, and a supernova, which is an explosion that expands and cools with time, is that unlike supernovae, which tend to get redder with time, TDEs have a pretty constant color. So this here is showing the rate of color change. And you can see that the TDEs, which we've identified in diamonds here, are basically at 0 compared to the supernova 1A, which definitely dramatically cool with time. We also use the rise time and the decay time. So tidal disruption events typically have longer time scales. And then of course we have the mean color, and the TDEs are bluer than a lot of the other transients, including variable AGN. So
how clear are we on the facts that you just mentioned? So the theory for this is not very clear. So this is all based on observations, but you are trying to select which are the TDEs, but
yeah, so basically you have a sample of photometric transients, and then you need to make your decisions on what you're going to take a spectrum of. So based on, and we do have a lot of spectroscopic capabilities, especially because of SEDM, which is the low resolution spectrograph. And so these symbols are solid if they've been spectroscopically classified. So We didn't originally, we're both selecting on these properties, but also taking enough spectra that to confirm that in fact the TDEs really do have these distinct colors and light curves.
So you basically use your gold standard as the spectra,
Yes,
and then based on that, you have learned that the colors
Yes.
are this and that.
yes,
Now you can select mostly on the color.
basically. Thankfully, ZTF, especially things like the Bright Transient Survey, because we're a community that's interested in all the transients, we learn from each other. So there could be, like, let's say we were too narrowly focused in one color range. We're taking spectra of so many transients that we would know if we missed one. Yes.
What is the typical parent magnitude range of the ZTF sample of TDEs? Are they
So-
like bright enough for SCDM?
Yes, so SEDM's limit is around 19th magnitude. The detection limit of ZTF is 20.5. So yes, there's definitely the brightest TDEs are going to be the rarest. But we certainly, the 30 TD, 15 TDEs per year is basically at a limit of 19.5 peak. But with Rubin, we're really going to be in trouble because now our detection limit is 24th magnitude. And so the you really have to think about if you're even going to bother to do a lot of spectroscopic work. And then also the samples are going to be huge.
All right, so one of the kind of exotic scenarios that Itai mentioned is this tidal disruption of a white dwarf,
Yes.
which can trigger a 1A, right? So I guess with this method, you wouldn't see any of those, but are there any other like searches for that are happening specifically?
Yes, so we have already done a search of the ZTF transients to look for the thermonuclear supernova that might be produced by a white dwarf being disrupted. The issue is that the rates are low enough and the expected, and they're faint enough that we've calculated that we really need Rubin to be able to get to the survey volume to actually discover a white dwarf TDE. And because the accretion signatures, if you use all those equations to figure out what the characteristic timescales for a white dwarf is, it's very fast. It's minutes. And LSST is not going to have that type of cadence, and it's also going to be very hot. So those events are going to be very UV X-ray bright. So, but the thermonuclear supernova that gets produced is optically bright. So you can search for them by sort of looking for peculiar 1As. And that's what we hope to do with Rubin. And it should detect maybe tens of those. Yes.
Is it known how those would be peculiar?
Yes. So there's a nice study by Morgan McLeod et al. 2016. Sorry, I don't have those slides here. I can get them if you want. That both does the light curves of the supernova as well as the spectra from the white dwarf. And they're supposed to be a little bit subluminous. And one of the most fun observational properties of a white dwarf TDE supernova is that you would see the velocity offset from the orbital motion of the disrupted white dwarf that had the explosion. So this is kind of a visualization of in the early days of ZTF, how we were having this sort of avalanche of transients and how we kind of filtered down from even just taking just the nuclear transients. It's a lot to deal with. And then removing what you know already are AGN from catalog matches, and then making sure there are enough detections. And then you start whittling down based on color and rise time. Then you get to a manageable amount to do spectroscopy. So each of you in your future projects with Rubin, you're going to be making your own decisions on how are you going to, or how is AI for you going to manage this torrent. And maybe, but either way, there are ways that you can get to relatively manageable rates. So these are some examples of the galaxy. Yes.
Sorry, just a quick question. The R band and G band cut here, how is that different to the like having 3 R band and 3 G band? What is it that they have to be pairs or?
So ZTF takes the G and R band on the same night. So I don't know why there would be, unless it was too faint in one of the bands, and so it gets rid of, you basically want to have a good light curve in both bands. Yeah.
Sometimes you'll get just R band data for twilight targets.
Okay.
The survey will start observing an R sooner than it'll start doing R and
Okay.
G.
And for the cuts we were doing, color was so important, so you wanted both. So here's some hosts of TDEs from the ZTF survey, and they have some common properties. And one of the interesting things has emerged is that they seem to prefer galaxies which are in host galaxies which are in this green valley, which is called a valley because that's where the least number of galaxies are in this color mass space. But that seems to be where the TDEs like to be, and they also seem to prefer nucleated galaxies. So that makes sense with higher stellar densities. And so this was a nice look at the relative rates between the red and green and blue. And you can see there's a much higher frequency of TDEs in green galaxies relative to blue galaxies, for example, in the same mass bin.
We have a question back
Yeah.
What does it mean for a galaxy to be green? Like basically the fact that like most of the TDs are leaning towards green valid and like.
Yeah, so green, this is just sort of astronomer speak, but this is the blue cloud of galaxies, and that is the red sequence. Color tends to trace star formation activity. So the red galaxies are red and dead. They have older stellar populations, whereas the blue galaxies are still forming stars and have different morphologies, maybe more disky and irregular morphologies. And there's a whole field of galaxy evolution trying to understand why galaxies go from blue to red, but they think it has to do with sort of a galaxy evolution sequence. And so this green valley is a valley because in the density here, the shaded region is the control sample from Sloan. So the green valley is, there's the fewest number of galaxies in this sort of transition region where maybe star formation is shutting off, or maybe you have other factors. Another interesting property of a lot of these host galaxies of TDEs is they seem to be post-starburst galaxies, meaning there was a burst of star formation, and then it seemed to have been shut off. And that's been connected to a post-merger system. And so where the merger both sort of triggered the star formation and then shut it off. And so there's some sort of potential connection between sort of the global properties of what's going on in the galaxy and then what's going on in the very nucleus of the galaxy to feed the TDEs. But people are very interested in sort of, is there a connection to binary supermassive black holes and things like that? But this is a very interesting area of study, understanding the host preferences.
So like knowing that, as we know about green galaxies, why does it lead to a higher rate of TD?
So one idea is that a post-merger produces a highly nucleated stellar density. So it might just be you're picking up these the galaxies that have the higher stellar density, so that'll feed more TDEs events. There are dynamical properties of stars orbiting a binary supermassive black hole that can cause periods of enhanced TDE rates. And then there are also fun aspects of understanding, why are the rates in the blue galaxies lower? Could that be due to dust obscuration, sort of just an observational selection effect? Or there's also this issue of the black black hole occupation fractions, and maybe not all of the low mass galaxies even have a black hole in the center. So there are all sorts of fun things you can probe. And then what's nice is we also see that we don't see TDEs in the most massive galaxies. And that, again, makes sense for this upper limit of 10 to the 8 solar masses on the central black hole mass. I just want to show some of the light curves that we're getting from ZTF. You can see we have very nice high cadence light curves. And this is showing typical absolute magnitudes. And you can see there's even a population of featureless and overluminous TDEs that have emerged. But you see they have very similar, there's a relatively narrow range of absolute magnitudes between -18 and -20, and these sort of nice declines with time. But there's also, this is another paper showing some of our TDEs, and you can also see that there's some really interesting structure in the light curves. So not all of them are exactly smooth. And so these, again, could be related to some of these messy effects going on as the debris streams settle into a disk. So perhaps we're seeing some signatures of stream-stream collisions or other activity.
Can I ask?
Yeah. Yes.
So on the previous plot, you showed R band, which I realize we measure, and then on the right you show black body, which is based on, I assume, some fit.
Yeah.
So
UV optical.
my question, which I wondered for a long time, is how are we seeing the peaks of these black bodies? Do we believe they're black bodies? Can we actually infer the total luminosity from the fits, and what is the uncertainty in that? I guess that's.
Yeah, so there's, we're getting the UV from Swift. And so those are, so in the game of fitting black bodies, when you only have optical data, you tend to get lower temperatures than if you have optical and UV data. And so there is likely some selection effects where it may be that even the near UV information we're getting from Swift may still be underestimating the true temperature of the emission. And then there's the fact that there's this additional soft X-ray component, which at early times, which you can sort of connect with the UV optical to get this sort of broader SED, which then would change your luminosities. But this in general is just the thermal component fitting to the UV and optical.
Because I think there's a lot of theoretical models that would predict that it should, radiate at Eddington or something, and so whether this decline is due to the actual volumetric luminosity dropping, or whether it's due to the effective temperature getting hotter and we're losing more flux in the optical UV, and that's sort of, anyways, I think that's an important question.
Yeah, and in general, the temperatures are relatively constant or get a little hotter. So that's not really, I would say that's not really driving the decline that we're seeing. Yes.
Just a comment
Yeah.
on what is being discussed here. At least in our simulations, when we compute spectra, we find for the prompt emission, we find that the peak of the emission is in fact in the extreme ultraviolet.
Right.
And so that here we are not, so that in optical we are not getting out most of the radiation. So if you use a black body, as you said, in fact, you would infer probably a lower temperature than
Yeah.
actually.
I'll show some of the broader SED models when I talk about the X-rays. And then We-
I have a question.
Yes.
You go back to the previous slide, so here, I think, one after, yep. So basically there is, I see like a few lines where there is a double peak
Yeah.
feature. And like, is it like classified as like one TD or is it like repeating? Like that's what we're seeing.
So these we are calling, these are kind of rebrightening events. This paper came out before we had some of the really neat repeating TDEs that have come out recently where you really see two big flares. Like this one here is pretty dramatic, but the amplitude is still much lower than the initial one. So we called those rebrightening, but it's possible you could interpret it as a repeating TDE. Maybe you could look carefully at the light curve. Yeah.
Just another quick question about the discussion on volumetric luminosities and so on.
Yeah.
So if you were to plot the black body radii, you said that the temperature is more or less constant, but it goes to the fourth power. So
Yeah.
How would the radii evolve?
I'll show you that. I'll talk about radius 1 second.
Okay.
So again, I claim that we know how to classify tidal disruption events from their spectra. And this is really powerful because, again, AGN vary, which I'll show you tomorrow, but AGN have very specific signatures in their spectra. And TDEs really are distinct. So they show very blue continuums and extremely broad lines in hydrogen and helium, as well as some fluorescence features. And so Bowen fluorescence features of nitrogen 3. And so they really can be, if you have the opportunity to take a spectrum, you really can distinguish them. And there's even a class now that's emerged that we are calling featureless that really don't show any features, are just very smooth. And we've done some population studies of the various spectral classes trying to understand what's driving this diversity in the spectra. And I just want to show here another nice plot. This is from Nickel et al. Showing the different strengths of this broad hydrogen and helium-2. Sometimes you see blue shifts of the helium-2, and as well as these Bowen fluorescence narrow lines. And the shapes of the broad lines are really, really interesting. They show changes with time, and they also sometimes show double peaked structure. And so we don't really understand exactly what is driving these line shapes, but it could be due to outflow, electron scattering in an outflow, or even from emission from a disk, and actually fitting these double peak due to the Doppler motion of the atmosphere of a disk. So this is all sort of frontier. We have these beautiful spectra and amazing line shapes, and we're still trying to understand what they're probing. But they are probing the this disrupted debris and how it's accreting onto the black hole, as well as the chemical composition of the star that was disrupted. And we're in trying to understand what's driving the widths of the lines. There doesn't seem to be an obvious correlation between the width of the line and the black hole mass, which is what you'd expect if it was dominated by virial motions, by the gravitational potential of the black hole. But we do seem to see a correlation between the width of the line and the optical to X-ray ratio, where that's tracing the amount of potential obscuration of the system. And so potentially the ones that have the broadest lines are also the most X-ray weak and have the most obscuration. And so it could be potentially a signature of electron scattering in this obscuring medium that's driving the line widths. So by curating these careful samples of spectroscopically confirmed tidal disruption events from ZTF, we can then start looking at their ensemble properties and trying to look for correlations or lack thereof. And so one obvious correlation we would be interested in is, with the black hole mass, do the timescales that we see in the light curves actually correlate with the black hole mass? Now, you may be wondering, how do you know what the black hole mass is? Well, I certainly, this is an indirect measure, but I'm using the host galaxy properties based on what we know from dynamical studies. I'm using either the host galaxy bulge mass or the velocity dispersion of the host galaxy. And so I'm inferring what the black hole mass is and then seeing, well, how do the properties of the tidal disruption flares correlate? And so one nice thing is that it does look like the decay time, this is T1/2, that's the amount of time it takes to decay by half of its peak flux, does seem to increase with black hole mass, which Itai derived the fallback time, which scales the black hole mass to the 1/2 power. I think this is what that theoretical scaling is. The actual relation is a little shallower, but it appears to be correlated. So maybe we can, in fact, use the light curves to probe black hole mass. There was a comment on the Eddington ratio. It looks like there's some sort of potential trend here in Eddington ratio with black hole mass. But I do want to point out that the luminosity distribution of the TDEs is pretty flat. So there's not a lot of strong dependence with black hole mass. Okay.
Yeah. Whenever I see this, I hear this, but then I see, to me, it looks like that there is a trend that it's.
Yeah, there is. Oh, which one? Of luminosity or what?
There's a cloud, yeah, but then, there's nothing in the upper left-hand corner or the lower right.
But these are a distinct class that are at higher redshifts, and so we don't have a complete sample of them. So.
Okay, so you're saying that maybe there's a selection.
They may be
regions that may
different,
be
yeah.
By selection.
But I will show you there appears to be a correlation with luminosity and mass that was later, just recently reported by Mummery. So maybe we can compare those relations. So the rates of TDEs, again, should be showing this characteristic fall off due to the presence of the event horizon. And in fact, as early as 2017, by looking at just, I think, 12 TDEs from various surveys, Van Velzen showed that, in fact, this rate was falling off at higher masses. And now with our nice ZTF sample, again, we see this nice precipitous drop off above 10 to the 8 solar masses. Okay, so there have been several surprises along the way. And one interesting thing is we really see in this thermal emission that we discover in the optical surveys, and then the thermal emission we're discovering in the X-ray surveys, which I'll talk about, there really seems to be this dichotomy of characteristic temperatures, where the UV optical has these temperatures that are much cooler than you'd expect for the accreting debris disk, this bare disk idea. And then the X-ray selected TDEs appear to be a little hotter, so really coming from the inner regions of the disk. And so this is showing you what the inferred radii are for these various components. And it really does look like the UV optical component seems to be tracing emission from material at much larger radii that are consistent with this intersection radius of the debris streams near apocenter. Whereas the X-ray radiation really seems to be tracing closer to the innermost radius of the the black hole. So again, you heard about these potential models for what's powering the optical emission. Is it again from the stream-stream collisions themselves and their associated outflows, or is it all related to the accretion activity onto the black hole and then its outflows and jets and other structures? So we've been observing the optically selected TDEs in the X-rays with SWIFT and XMM, and we find that they really show uniform properties in the soft X-rays. They really show these extremely soft thermal spectra. You'll note there are basically very few photons above 1 keV. So this is also a signature that's very distinct from AGN, which have a power law continuum in the X-rays that can extend to tens of keV. They're really bright and hard X-rays, whereas TDEs are unique for being extremely soft. And it turns out that QPEs, which Itai briefly talked about, are also very soft in the X-rays, but TDEs were sort of the first interesting soft X-ray source. And while they have these uniform X-ray spectra, their light curves in the X-rays show lots of diversity. So some of them decline nicely as a power law along with the UV optical emission, and others show dramatic brightening at late times in the X-rays after being initially faint. So we want to understand sort of what is driving this diversity in behavior. And one idea is that this is due to reprocessing of the innermost X-ray radiation that sort of produces an excess in the UV optical. And also that this sort of could be very dependent on viewing angle. And so in the dynamic picture of the X-rays brightening over time, you need somehow for your view into the accretion flow to be changing. So that can be due to the funnel sort of widening or the density of the material outflowing and getting less dense, so you can actually start to see the X-rays breaking out. There's also an idea that maybe the X-rays intrinsically aren't there at early times, and this is due to a delay in the debris actually circularizing through these stream-stream collisions to form a disk. Okay, so one thing that was mentioned that's really exciting development is while this early phase of the TDE, which Itai set up, of the star being disrupted and the streams then self-intersecting, that process is messy and has, timescales of a few years. But we're seeing at late times, if you look at these older TDEs or you continue to follow them for years later, they all seem to be reaching what we're calling a plateau state, because especially in the UV and optical, if you look, they appear to be really flattening out in their light curves. Now, the only way we could know this is by this nice long baseline of the ZTF survey, which again has been operating since 2018, and then also continuing to look at the TDEs in the UV with SWIFT. And this plateau here actually is the expectation for how a spreading compact disk evolves. And so so that's the UV optical light curve. But if you look at the broadband SED of these TDEs in this late time phase, and you combine the UV optical data from ZTF and SWIFT with the X-ray data from SWIFT and XMM, and then you connect the UV optical and the X-rays, you get what you can fit with a multi-temperature disk model, accretion disk model. And now with this disk model, you can actually solve for the peak temperature of the disk as well as the outer radius of the disk. And you can see that the disk fit to this, this emission results in a disk radius that's basically consistent with the circularization radius for the size that you expect for the disk from the debris streams. So this is really nice. So this is really showing first that TDEs really do eventually form a compact accretion disk. So the black hole is accreting the material, and that the size of the disk is consistent with the size of the disk formed from debris streams in the tidal disruption event. So that's a really neat result. So turns out that we see this in a large sample of TDEs now at late times, and there's both theoretical predictions for how this, the luminosity in the various bands of this disk emission should scale with black hole mass, with a spread due to, I think, mostly the spin of the black hole. But you get this nice correlation between the plateau luminosity in a single band and the black hole mass. So now all of this work we've been doing to characterize the tidal disruption event light curves and get their spectra and everything yielded this wonderful sample that now is telling us, oh, you can be totally lazy and come back a few years later and just measure one luminosity in one band, and I can give you the black hole mass of that event. So that's pretty fun. Yeah.
I was trying to remind myself. So what are the different colors in this? On the left
This is
hand?
time.
Okay.
So I think it goes yellow to brown. So it's cooling.
Yes.
The disk is cooling, but the outer radius is basically the same. I think this spread is due to the uncertainty in the data. Okay, I just want to briefly mention that there is a subset of TDEs that show strong, bright radio emission that's interpreted as on-axis synchrotron radiation from an on-axis relativistic jet. There have been a few discoveries. There were initially a few discoveries early on by Swift of these events selected in the hard X-rays. But there was actually recently a optical discovery of a transient, which then from follow-up was shown, this was discovered by ZTF, but in follow-up was shown to have very bright radio emission consistent with these jetted TDEs, the most famous one being Swift J1644. And, but we're also seeing that but only about 1% of tidal disruption events show this very strong on-axis bright radio emission. But we are seeing, by monitoring our optical TDEs again, we are seeing that they in fact also show radio emission, but sometimes years after the initial event, and then show this remarkable brightening at late times in the radio. And so this is a really exciting field with lots of questions. Is this the delayed launch of an outflow? Is it a change in accretion state? Or are we starting to see an off-axis relativistic jet? Okay, so I've talked a lot about optical selection of TDEs, but we've had this wonderful new window onto the soft X-rays with eROSITA, which unfortunately is no longer operating. But it picked up its own sample of tidal disruption events. Now selecting that soft X-ray emission that we've shown is also seen in the optically selected TDEs. But just by looking at the soft X-rays, they've picked up a sample. This was the first paper that showed about 12 TDEs, I think, from Rosita. And again, they seem to be preferring this green valley in the color galaxy mass diagram. And we can sort of combine the optically selected and X-ray selected TDEs and use their X-ray luminosities to actually get an X-ray luminosity function. And then this is a more recent paper of a larger sample from Rosita. And again, they seem to be preferring the Green Valley. Okay, we also have this phenomenon of the dust echoes from TDEs. And this has been discovered from the all-sky imaging in the mid-infrared by WISE. And it was first found by looking in the WISE data at the positions of some older TDEs, and they showed this delayed flare in the mid-infrared. And from looking at the infrared luminosity, you can infer the covering fraction of the dust. And a kind of nice result is that the covering fraction of TDEs of dust is less than 1%. And this is much smaller than the type of dust echoes we see in AGN. In AGN, this is the cartoon picture of an AGN, but they appear to have this large dusty torus around them. So when they do an infrared echo, they have a much larger covering fraction, more luminous, whereas the TDEs seem to be sort of picking up sprinklings of dust that just happen to be near the nucleus of the galaxy, but aren't in this well-organized structure. So given that we saw these dust echoes from TDEs, it was then realized that why don't we just go ahead and look in the mid-infrared for flares and see if we can just select TDEs purely on the mid-infrared. And this is a really nice plot from Masterson where you see the WISE light curves in blue and the optical is just flat. Almost all of these are completely obscured in the optical. So the only way we could know about this flare is from its dust echo in the mid-infrared. And so this is a sample of TDE candidates. And you can see their host galaxy preferences. And some of them are actually starting to probe higher mass galaxies, as well as some more star-forming galaxies. Yes.
I have a question.
Yes.
I missed something, but how do you know they are TDs if you don't see the optical?
So they have host galaxy spectra. So none of them are obvious AGN, but I think there can be some ambiguity. But I think from the host galaxy properties, they argue that they're at least not AGN. And too luminous for supernovae. What?
And they are consistent with coming from the center of the galaxy, or you don't have the resolution?
I don't think you have that type of spatial resolution. Yeah.
No, these are all in the centers of the galaxies, like within an arc second or something.
Right.
And they're very luminous. The total radiated energy reaches like 10 to the 52 arcs just in the mid-infrared. So these are very luminous eruptions happening right in the centers of galaxies that are not AGN. So these can't be supernovae because the energy budget doesn't allow for that. So the most likely explanation is that these are TDEs.
Now, AGN also show beautiful dust echoes, and you will pick those up as well. But I think the ones they're highlighting here are the ones that have the most secure lack of AGN activity.
Wouldn't the AGN activity also be obscured?
You mean in the optical spectrum?
Yes.
Yes.
So you say they don't show AGN activity from which indicator?
From everything we could find, which is WISE colors, optical spectroscopic lines. Yeah.
And this is just an example of sort of this new window onto TDEs by looking in the mid-infrared, where again, they discovered a very nearby TDE that we were completely blind to, and the optical is completely obscured. And this is the same one, and you can see that this host galaxy appears to be quite blue in comparison to some of the other samples. So it's really sort of highlighting the importance of observational selection effects as we look in these different wavelengths. Okay, I wanted to briefly talk about neutrinos because your module activity talks about localization of very high energy neutrinos with Rubin. And I just wanted to let you know that we now have a few secure associations of very high energy neutrinos from IceCube with astrophysical sources, and in particular with accreting supermassive black holes. So the first sort of multi-messenger detection of an IceCube source was with a known blazar, shown here, TXS 0506, which was in the localization region of the neutrino event, and also showed interesting variability. And then right now there's by collecting all the data, there's a hotspot in the neutrino map associated with an AGN, a type 2 AGN, so that's an obscured AGN, or sort of it has this dust torus is obscuring the view of the very inner regions of the AGN, NGC 1068. So again, associated with a subclass of an AGN. And we had a association with a very high energy neutrino with what we had been studying that we knew was a tidal disruption event. This is AT 2019 DSG, which was in the circularization window. But what's interesting is that the neutrino actually arrived almost basically half a year after we discovered the event with ZTF. But this TDE is also unique for being quite radio bright, as well as X-ray bright. And so this was very intriguing. And since then now we have 3 optically selected and 2 mid-infrared selected nuclear accretion flares that have been discovered. These are sort of a combination of TDEs and AGNs that all appear to have strong dust echoes that seem to be in the same region of these neutrinos. And so this is showing all 5 here, where you see in the optical a flare, or in the case of these 2, the optical is totally obscured. You just see the mid-infrared flare, but all of them show a strong mid-infrared dust echo. And interestingly, while the neutrino arrival time is delayed with respect to the optical flare, it appears to occur close to the peak of the infrared dust echo time. So there have been some work by theorists trying to see if maybe it's the infrared photons from the dust echo itself interacting with the high energy particles to produce these neutrinos. Okay. I did want to talk about this exciting new phenomenon of repeating and rebrightening TDEs. Sorry, I haven't really been pausing for questions, but I assume you guys will interrupt me. Oh, you have a question? Yes.
How are the protons accelerated in the TDE?
So there are various sites for which they can collide, but you need the energetic particles, I think, to be produced by some sort of relativistic jet. And then they interact with the photons coming from the echo. So the top is really a beautiful example of a repeating TDE from E Rosita, which shows this cycle of rebrightening episodes. And on the bottom is a famous optical repeating TDE that shows this very dramatic brightening in the optical, but it's seen across all wavelengths. So these really are potentially explained by the repeated partial disruption of a star in a bound orbit. And these really are multi-wavelength phenomena. So they kind of look like normal TDEs, but they're repeating, and they really emit in the X-rays and UV and optical. But there's this new phenomena that is specifically only in the X-rays, and these quasi-periodic eruptions. And here you see this beautiful X-ray light curve where you see these repeated eruptions. This was first discovered in 2018 by XMM Newton. And since then, they've been searching for QPEs in the E Rosita data. And there have been 7 more QPEs discovered. And this is showing you their various properties. So you have the duration of the eruption of this flare, as well as the recurrence time in hours. So you can see that there's a wide range of recurrence times, and there might be a correlation between the recurrence time and the duration of the outburst. And they all seem to have, interestingly, galaxies which have host masses which are in this regime that should look familiar. This is the 10 to the 6 to 10 to the 8 solar mass black hole regime, which is specifically where we find tidal disruption events. So it's very interesting that these galaxies, which are demonstrating the QPEs and the X-rays, have these lower mass black holes, and almost all of them are pretty much quiescent galaxies. So they don't have a very strong AGN going on. And I guess there was most recently another discovery of a 5th QPE from the E Rosita survey. So very interestingly, not only do these QPEs occur in galaxies with these lower mass black holes that are consistent with the sort of black holes that can disrupt stars, but they also seem to once again prefer these what we call post-starburst galaxies that have evidence of a young stellar population, but no very recent star formation, indicating that the star formation has been recently shut off. So there's a lot of parallels between the QPE host galaxies and the TDE host galaxies. Well, then we had an observational surprise, which Itai said he actually had predicted, which is really cool, which is, lo and behold, there's this beautiful TDE, very bright nearby TDE that we've been studying in detail. And it has this nice optical flare. And then look, it shows the plateau that I was talking about in the optical. And then it was being monitored in the X-rays, and then suddenly, boom, it started to erupt in QPEs. And if you look into, so this is where you really have to think about what is the cadence of your observations, what are the type of phenomena you can pick up with your surveys. So these QPEs just showed up as some brightening within the data, but then when you use the beautiful time resolution of NICER, at the NICER X-ray telescope, then you can see that there's a real structure in these brightening episodes, and they are in fact look a lot like QPEs. So why is this? How is it that a QPE turned in, or a TDE turned into a QPE? Well, like Itai said, they had this idea that maybe what's causing these eruptions is the interaction of an orbiting star with an accretion disk that was newly formed from a TDE. So basically, you need the TDE to produce a disk that can then interact with this very compact orbiting star. And I show some various diagrams of that interaction, but there's also ideas that maybe it's in fact just accretion instabilities of the accretion disk. And perhaps then again, you could have the TDE disk be the one that's having these instabilities. But there's a true connection there. Any questions? Okay. It's a lot of exciting things. So another really exciting new development is
Suvi, when you're on this topic, can you tell what are the fraction of
TDs that have QPEs?
Yeah, there's
yeah, go ahead. There was a paper.
Yeah, so this analysis has been performed by Johin Chakraborty following the discovery of another TDE that has hosted QPEs. So by now we have 3 such sources. So you can try and do some statistical inference of that. And they find that about 10% of TDEs are hosting QPEs, given the selection effects and so on. And I think this roughly matches our understanding of the dynamics that end up putting stars on these orbits, the dynamics that produce TDEs.
So I think it's been proposed that you could use something like AXIS, which will be a future X-ray telescope, which doesn't have the type of amazing area as eROSITA, but you could just monitor known older TDEs to try to catch this phase. Okay, so another really exciting development, which is why I love my job, is now we're starting to see off-nuclear TDEs. And in fact, it's kind of interesting. Again, this emerged mostly from looking at the universe in different ways. And so this was an archival Chandra detection of an X-ray transient. And this time it's not coming from the center of the galaxy, but it appears to be in the halo of a galaxy. And I forget in this, yeah, and I think there's the transient is associated with very small galaxy, maybe satellite galaxy. But I think this one, they weren't able to get the redshift of the X-ray flare, so it was a little tentative. But then Einstein probe, which is a new Chinese X-ray mission, discovered an X-ray transient here. And this is showing what the underlying optical looks like. And it's this very fuzzy, small galaxy. But again, it's sort of in the halo of this more massive galaxy. And then this is a beautiful result where ZTF they were doing their regular TDE routine, and they noticed that one of their TDE candidates seemed to be a little off nuclear, still past our filters, within, I think it was 0.3 arc seconds or so, but it seemed to be a little off nuclear. And then Yuhan Yao got beautiful Hubble imaging, as well as Chandra and radio. And you can confirm that indeed, this transient that we would normally just call a TDE is not in the nucleus of the galaxy. It is off nuclear. And this is a nice compilation from Yuhan's paper, where you can see these 3 off-nuclear TDE events that are appear to be associated with very small dwarf galaxies, only 10 to the 7 to 10 to the 7.3 solar masses. That's what you infer for these little fuzzy underlying galaxies. I don't know if you remember from my plots before of galaxy mass, we don't even see TDEs in our normal samples below 10 to the 9 solar masses. So this is really very low mass galaxy hosts, but they're not just, and then these 2 in particular, or actually all of them, have a parent galaxy. So in the halo of these very massive 10 to the 11 or so solar mass galaxies, which we know their black holes would be way too big to disrupt a star. So the black holes that we're seeing being lit up off nuclear are smaller black holes. And we think that their black holes are around maybe 10 to the 5th to 10 to the 6th solar masses. So you're starting to probe what we would call wandering black holes. So black holes that are not in the center of a galaxy, but have been found there either because of the interaction of an infalling satellite galaxy, or from the interactions of the central massive black hole and other black holes that might slingshot another black hole if it's a binary system and a third body comes in, or if you had a recoiling black hole following a merger. But I think from radio studies that they can conclude that this black hole, this galaxy actually has a black hole accreting. And so this smaller black hole can't be due to gravitational wave recoil, because then you wouldn't have a black hole here anymore. But it's very interesting. These are sort of lighting up these wandering black holes, smaller black holes that give you insight on sort of the dynamics of black holes in the universe as galaxies are interacting and colliding. Okay, so I wanted to finish today with a nice little exercise in trying to predict what Rubin is going to do. So I just said all these exciting results from ZTF and eRosita. Why do we need Rubin? We already have this beautiful diversity in TDEs. But remember, we still only have about 100 or so TDEs right now, and we're just starting to pick up these other exotic populations. But I really like this paper by Ramsden et al. Recently, where they just tried to forecast what Rubin will discover for TDEs. And while a lot of people have talked about the rates of TDEs by Rubin, you'll hear numbers like thousands per year. I really like this paper because it looked specifically at the mass distribution of the detections by Rubin. So what they did was a simple argument. First, they started with a Schechter galaxy mass function. So we have a very good understanding of how the volume density of galaxies as a function of their mass. So the most massive galaxies are the rarest. Then we know from dynamical studies of black holes in nearby galaxies that there is this relatively tight correlation between the mass of the black hole and the mass of the host galaxy bulge. So we know what the galaxies look like. We have this scaling relation. Now we just have to get from galaxy mass to bulge mass. So they use the average properties of Sloan galaxies, their bulge to total ratios, as a function of galaxy mass. Okay. So then now you can go from a galaxy mass function to a black hole mass function. Then you need to assume the mass function of your stars. So they use a Krupa stellar mass function. They need that because you need to calculate the upper limit to the black hole mass that can disrupt a star. So if you can actually observe it. And then they assume a spin distribution of the black holes because that affects that upper limit as well. And then they use this really nice relation. So Brian was saying, well, there is, I think, a relation between black hole mass and peak luminosity, but basically this is from Mummery et al., where I think they're using, I forget where black hole masses are from the host galaxy relations, but they see this relatively strong correlation between luminosity and black hole mass. And you can see there's a little bit more points here than fewer here, but they argue that there is some empirical relation here. And so if you have your black hole mass function, and then you know that what the peak luminosity will be in the G band of the flare, then you can use the flux limit of your survey and just say, okay, well, so what is the rate of events and will it be bright enough for me to detect it? And I think they assume 1 magnitude above the detection limit is what you need to be able to follow it and identify it. But what's really neat here is that shown in gray is just this overall distribution of black holes that we expect in the local universe. And you can see that the majority of black holes are these smaller black holes. That's because the majority of galaxies are the smaller galaxies. Then you say, well, I can't see anything from the very big black holes because of this maximum mass. So I use that Hill's limit and get rid of those ones that are unobservable. And then I say, well, given these black hole masses, what is the expected flare luminosity? And then I say, would I be able to detect it? So this green line is what you'd expect for ZTF cutting off where you need your flare to be at least 19 and a half. Oh, gosh, sorry. At least I didn't fall. 19 and a half magnitudes. And what's so amazing, just shows how important it is to understand your selection effects. While the universe is teeming with these lower mass black holes, we think, I'll talk about some uncertainties in that in a second, we actually only have the capability with ZTF to observe this upper end above 10 to the 6 lower masses just because based on this empirical relations, they're just too faint for ZTF to detect. But what's so exciting about Rubin and why all of you guys should drop everything you were doing if you're studying planets, exoplanets, forget about it. These Rubin, because it's so faint, it goes so deep, we're suddenly picking up all of these lower mass black holes below 10 to the 6 solar masses. It's going to be just routine. It's just sort of the main sample is going to be dominated by the lower mass black holes. It's so dramatic. It's so exciting. Now you have to figure out how we're going to identify them because they're going to be faint. And so you're not necessarily going to have spectroscopy, but maybe you don't need to take a spectrum of all of them. Maybe you just need to take a spectrum of 20 of them and you're going to learn something. But that is really exciting. But then there's also this complete uncertainty on what the actual black hole mass function is at lower masses. We just assumed everything scaled all the way down. And we also don't know if every galaxy has a black hole. That's this black hole occupation fraction, which is really exciting for understanding supermassive black hole formation. So I think this is just really, really, really cool. And just for fun, I was just looking at, this was like a compilation of about 94 TDEs from the Mummery papers. And it's just showing you the black hole masses. But indeed, they are peaking here between like 10 to the 7 and 10 to the 8 solar masses. And we're not sensitive to, we're not getting to these lower mass galaxies with the lower mass black holes yet with ZTF. Yes.
So I don't know what these, maybe I should speak into the microphone. I don't know what these papers assume, but it seems to me that as you go to higher redshift since TDs are so blue, that's going to help you a lot in terms of the redshifting. And then also, if really these things are tracing, merging galaxies and the rate of mergers is higher, redshift 2, it seems like the rates will just kind of take off as we push from detecting these at Z of 0.1, 0.3 to Z of a few. But I don't know what these, is that sort of uncertainty still lingering there?
Yeah, so Mitchell Carmen, who is my graduate student at Johns Hopkins University, his thesis is exactly to show the exciting ways we can trace TDEs at high redshift, and he's studied all these various effects. Yeah.
Okay, all right. I'll show you some plots. But I guess my question is.
But you're also battling with the black hole mass function is also, the black holes are also getting, are less numerous in the mass range that you're interested in, but there are all sorts of exciting effects like density, higher stellar densities, higher merger rates. The K correction helps you. Yeah, so we think that Rubin will be really exciting for probing the black hole mass function by looking at the evolution with redshift.
Maybe I have one more question, which is just, you mentioned these scenarios, these possible ways of TDs either trace stellar density or they trace black hole mergers.
How do you
and
tell?
I'm going to guess that those are going to have different dependencies on redshift, right? So you're saying that we can also probe those. Okay.
Yeah. Okay. I'll just conclude with once we find all of these TDEs in the optical with Rubin, we're going to be, we just have to wait a few more years, but we'll be in a really rich ecosystem because in addition to the optical from Rubin, we're going to have these powerful ultraviolet observatories. And I haven't talked a lot about the ultraviolet, but TDEs are the brightest in the ultraviolet. In fact, they're the most luminous transients at ultraviolet wavelengths. And the UV is really, really valuable for identifying TDEs because unlike supernovae, which are only bright in the UV for maybe hours to days, and they really decline quickly due to their expansion and cooling, TDEs are just beautiful, long-lived UV transients, and then now they have this really long-lived UV plateau that we know about. So it's really easy to pick up TDEs in the UV, and I would argue that if you had Rubin operating and then you had co-observing, which we will have with Ultrasat and UVEX, you can just simply look at the UV optical colors and decide that something is a TDE. So Ultrasat, which is an Israeli mission that's going to be launching in a couple years, is going to produce really beautiful near UV cadenced imaging on various timescales from a few days over the whole sky to cadences as good as 5 minutes over one field of 200 square degrees. So kind of like tests, like quality light curves, but in the UV. It's going to be really spectacular. And then UVEX, which is launching in 2030, it's the next NASA Medium Explorer mission. This is going to provide not only all sky far UV and near UV imaging, which you can use to discover tidal disruption events, as well as pick up all these beautiful UV plateaus, but it's also going to have UV spectroscopy with rapid response. And I didn't talk a lot about the UV spectroscopy of TDEs, but they show really exciting features that, again, are very distinct from AGN. And so it's a really powerful probe of them. And so these new UV and optical telescopes are really going to be factories for discovering and characterizing thousands of TDEs. And I think I'll just conclude with this slide, and then I can take any last questions. a lot, I know. Yeah.
Could you explain how nanograv is going to pick up TDs?
So nanograv is sensitive, that's the pulsar timing array, is sensitive to the more massive galaxies, massive black holes, so above 10 to the 8 solar masses. However, you can relate, let's see, what's my argument for nanograv? I mean, you're going to detect massive binary supermassive black holes. You could do things like, what is my multi-messenger argument for nanograv TVs? Hold on. I don't really have that much of a multi-messenger. I always say, like, you could potentially pick up an enhancement of TDEs around, you could pinpoint binary supermassive black holes that are producing TDEs, but those again will be the lower mass black holes sensitive to LISA. So there's not a lot of joint, but it is going to be studying supermassive black holes, but yeah, bigger than can have tidal disruption events, unless you're looking at red supergiant or red giant disruptions. Yes.
I'm sending you back a bit to the X-ray observations.
Okay.
What do you see in the X-ray observations in terms of both absorption and a change in the cutoff? Because I guess if the medium is has very high column densities, I would expect a kind of sweep due to Compton degradation, where like you would, start off with a cutoff that's lower, and as you sweep to lower column densities, gradually get a higher energy cutoff.
Yes.
And if it's a lower column density, you get something similar where the absorption feature is kind of shrink. I don't know how easy that would be to do below 1 kV though.
Yeah, so we don't see any of the standard X-ray absorption features associated with sort of neutral gas, but what they have been able to do is explain the suppression and flux due to some sort of gray scattering, potentially like a ionized medium where you're just dealing with electron scattering. But the typical sort of X-ray shapes that you'd expect, from looking at obscured AGN and things, we do not see. Yes, in fact.
Just about the delayed radio brightening we see, is it just synchrotron radiation, and does it come with any emission in other wavelengths as well, or is it just the radio?
There have been some suggestions of correlations between radio and X-ray emission. I think maybe in Assassin 14 Li, there were some arguments, but in general, it seems like this radio brightening is completely uncorrelated with what's going on in the UV and X-rays. Although I think there was a recent paper that argued that maybe it was signifying a certain threshold in the accretion rate, so that you're seeing the radio emission once the accretion rate declines to a certain value. But it doesn't seem to be directly correlated with the other wave bands. Yes.
Can you say a bit more about neutrinos from TDs? Like how many have we seen and how many events?
Yeah, so there are total of 5. These are the 5. Oh, I'm going to talk about Scary Barbie tomorrow. Do you guys know who Scary Barbie is? You're going to find out. Because Scary Barbie was also associated with a neutrino. These are the 5. Now, to be honest, the neutrino community is a little skeptical of these associations because their reanalysis of the localization regions is slightly different than what was used in these papers. And also, physicists are in general not happy about the delay between the event and the arrival of the neutrino. While these models are trying to infer that maybe you need the infrared photons. So first you have to illuminate the dust, so you have some time travel to the dust to explain things. But some people are not very satisfied with that. So I've talked to some neutrino observers and theorists, and what they've basically said is, we will believe you when we see a second neutrino from one of these events. So I think that would, yeah, so it's still sort of tentative.
Right. So if these neutrinos are indeed from the TDE, then, or they are like actually detected neutrinos, then is the low rate because of the like intrinsically rare neutrino, like event rate for neutrinos being produced, or is it like a sensitivity thing for neutrino detectors?
When you say which rate is low, the TD?
Like only some like very rare TDs produce neutrinos through this, IR target photon mechanism, or is it just that our neutrino detectors are not sensitive enough to catch this, and more TDs can actually produce neutrinos?
Ah, you mean like, what about our whole TDU sample? Weren't they all associated with? Yeah, so I don't know, how the sensitivity of the neutrino maps compares to the TDE sample. But the way the argument that Schuert Van Velzen made was that the thing that after you do these associations, the thing that ties all these events together, they're all accreting supermassive black holes, and they all have these very luminous dust echoes. So he was saying, well, maybe that's what you need, that's the ingredients. And then also they have sort of lower mass black holes so that the peak accretion rate is close to the Eddington rate. But that maybe those were the conditions. And I think most of them were radio detected. So maybe those were the conditions needed. But I think we need more associations.
I mean, I think if all of them made the same neutrinos, we would expect to see them from the closest ones. And I don't think these are the closest. So I think you have to look for some. That's